Now we'll be doing a sample problem for the compression member. And this problem, if you read the problem, it says that determine the design strength of the compression member W150 by 22. Okay, so this is our steel section, 150 by 22, and it's an A36 steel. The member is pin connected at its both ends, that's pin connected, and is laterally supported at the midpoint about its weak axis. Okay, so if there's a weak axis, it's gonna be the bending along this axis, okay, along this line. Okay, so that's our weak axis, y, and this will be our strong axis, x. Okay, so this is just an analysis problem, and the first step to do is to obtain the. Okay, so let's write our solution. So step number one is to obtain the necessary information. Okay, so meaning that we are to check the table or go to the property table. And you have to go to the W section and find the details about W150 by 22. Okay, so if you've done that, if you have your property table, and we'll check this, you'll find out that the cross-sectional area is 2,860 millimeters squared, and our depth would be 152 millimeter. What else? We'll also need our radius of gyration. So that's going to be Rx and Ry. For Rx, that's 65 millimeter, and Ry is 36.8. Okay, and we'll also need the information about the compact section. So the first one that we need is this. I think this is the unstiffened element, the flange, BF all over 2 times the thickness of the flange, and it's given us 11.5. And for our web element, we have H sub C, the thickness of the web is equal to 21.6. Okay, so the next step is to check the slenderness. Okay, check the slenderness. So meaning that we have to check the flange element and then the web element. So for the flange element, our condition, this BF all over 2 TF, it be the width of the flange divided by 2 TF. Is it less than or equal to our limiting width to thickness ratio, okay, for slenderness? And this one is just equal to 0.56 square root of E all over Fi. Okay, so you can find this in the table in our lecture handouts. And that's how we are going to determine um, if we have a slender element. And if you recall that we are checking the slenderness because it is we are checking if local buckling will occur before the overall buckling. Okay, so this one is 11 point. This one is 11.5, and this one 0.56 times square root of E. The modulus of steel is 200. I think that's 200,000 megapascal. And this one, since this is A36, then this is just 250 megapascal. Okay, so we'll check this one. 200,000 divided by 250 square root. That's 15.83. So 15.84. Therefore, flange is not slender. Okay, we'll just write flange is not slender. Okay, so now we'll check the web element. For the web element, we have this value 21.6, and we are going to compare that to the limiting width to thickness ratio. But the condition is, I think that's 1.49. Okay, so 1.49 square root of E all over Fy. This one is 21.6, and this one would be, okay, so it's just the same thing. Same value, 200,000 divided by 250 square root. Okay, we'll check again. 200,000 divided by 250. Okay, we'll take the square root times 1.49. We have 42.14. Okay, so therefore, web is not slender. Okay, so the next step would be to determine the governing slenderness ratio. Slenderness ratio. Okay, so to check, we are going to check both the x-axis and the y-axis. Okay, so for now, I think it would be helpful if we draw the member. Okay, so we have this pin connection. And this is along the strong axis. Is it a strong axis? That's x. And for the weak axis, there's a lateral support at the midspan. And the distance is 2.25 meters, and this one would be 2.25 meters, whereas this one is 4.5 meters. so this is weak axis y dash y. Okay, so since this is pin connected, if you go to the tables, I mean the effective length factors, you will obtain a value of k that's 1.0. So this also the same k is equal to 1.0. Okay, so we'll continue our computation. So this one we'll write klx all over rx. So our k is 1. That's 1.0 times the length in x. That's 4.5 or 4,500 mm. And our rx is 65 mm. Then for our KLY, we have, okay, so along the y-axis we'll have two distance. If in case in our homework we'll have I mean the lateral support is not along the midspan, then we will have a different value for the unsupported length. And so if that's the case, then we'll have to use the larger value. But here in the sample problem, it's just the same. So we can just choose whichever distance. Okay, 2,250 mm, and the radius of gyration is 36.8. Okay, so now we'll compute this one. 4,500 divided by 65, and that's 69.23. And this one, 2,250 divided by 36.8, that is 61.14. So therefore, the governing slenderness ratio is KLX over RX is equal to 69.23. Okay, so now we have to compare this governing slenderness ratio to our limiting value. This would be our step number 4. Compare the governing slenderness ratio. Compare that with our limiting value. The limiting value. Okay, so first we'll solve the limiting value. So we have 4.71 square root of e all over fy. So divided by 250 times 4.71. That's just 133. That's 133.22. And we see that our governing slenderness ratio is less than this 4.71 square root of EFY. So therefore, if this is the case, then our equation, our critical stress equation is FCOR 0.658 Fy all over Fe times Fy. Okay, we know Fy, but we don't know Fe, so therefore solve for FE. FE is computed by this equation, pi squared E divided by the square of the governing slenderness ratio. And that's okay, so we'll write it down, pi squared, and then this one is 200,000, that's megapascals. And this one is 69.23 squared. And we get a value of 411.85 megapascals. Okay, then the next step is to computing now the FCR. Okay, so FCR is just equal to 0.658 raised to Fy all over Fe times Fy. Okay, so Fy is 250 divided by our Fe, 411.85. That's gonna be our exponent, 0.658 raised to the value times the Fy, 250, and we get 193.9 megapascals. Okay, so that's our stress. And solving now for the design strength. Solving for the design strength. Okay, so for the design strength, the equation is just simply the strength in terms of actual loads, actual loadings. So it's just simply the reduction factor times the stress times the area. Okay, so the reduction factor for compression members is 0.9 times this one, 193.9 megapascals, times our area. Our area is 2,860 millimeters squared, times 2,860 times 0.9. And this is in newtons, so divided by 1,000, you get a value of 499 kilonewton. Okay, because we'll check again, 2,860 times 193.9 times 0.9. Okay, so that's our design strength. Okay, so in review, this is the sample problem. We first obtain the necessary information. So whenever it is an analysis type of problem, then we have to obtain the necessary information, because you know that the analysis problem means that you have the geometry, you have the details, the dimensions, and you just have to find uh, the strength. So we can obtain the necessary information by going to the property table or section property table, and we have to find this steel section W150 by 22, and we write down here the depth. Actually, we didn't use that, so you can just omit this one. So we wrote down the area, the radius of gyration, along X and along Y, and then the compact section. Okay, so it's 11.5 and 21.6. So after obtaining the value of the compact section, we then compare that to the limiting width to thickness ratio. So this one, the flange element, this is the limiting width to thickness ratio, and we solve that. And if it is less than, then meaning that the flange is not slender. If it's greater than, then the flange is slender. And if that's the case, then um, we we haven't discussed the detailed discussions or computations regarding those members with slender elements. So we'll just limit our discussion to compression members without slender elements. Okay, so flange is not slender. Then we also check the web element, and we check the limiting width to thickness ratio. And note that the limiting width to thickness ratio is different from the flange value. So this one is 0.56, this one is 1.49. Okay, and when we calculated, we found out that web is also not slender. So meaning that we have a compact section, and therefore no local buckling possibility can occur. Okay, so after that, we then check the slenderness ratio. Okay, so slenderness ratio, uh, in order to be able to comprehend, I mean, the various parameters, we we draw the details for both the strong axis and the weak axis. Now, for strong axis, we don't have lateral support, and therefore the strong axis we have this length, this 4.5 length. And for the weak axis, since it has a lateral support, then the unbraced length is 2.25 and 2.25 because this is along the wingspan. Okay, after that, um, we compute or we determine the governing slenderness ratio because we want to, to compare that to the limiting value. Okay, so this is the limiting value. If our governing slenderness ratio is less than this, then this will be our equation. But if not, if it's greater, then we'll have another equation. So just refer to our lecture handouts. Okay, so that was the next step. Then after that, since we knew that it is less than, then our equation would be this one. But to solve this, we would need the value of f sub e, wherein you can compute that using this equation. And we cut this value. So after that, you can now solve for the stress. That's 193.9 megapascals. And by having the stress, and you already have the area, you apply the reduction factor, and you can obtain the design strength. Okay, so I guess the computations for the analysis of compression members for members without slender elements, I think it's just pretty straightforward. So in the next video, we'll be moving on to our next topic. See you in the next video.